Hello, class. Welcome back. This is MO 869, Introduction to Autonomous Vehicles. Lecture 5. Today we're going to cover Lecture 5, which is Camera-Based Perception, Part 1. The outline goes as follows. Before we introduce you to various perception tasks and their details, I'd like to start with camera geometry and calibration, and then the following contents will cover the perception tasks. So camera geometry, the most widely used model is pinhole model to describe the camera parameters, intrinsic and extrinsic parameters. There are intrinsic and extrinsic parameters, and here we're going to introduce the intrinsic parameters first. So let's start with a so let's say there is a point in 3D space, and we have this focal point, and we have camera plane somewhere in the middle, and then we're going to define this this distance from the point to the plane as focal length f, and the depth would be the distance from this focal point to the actual point. And then we are going to define this P on the camera plane as XC, YC. What that means is it's a projected point of the capital P in 3D space on the camera plane. So let's take a look at some of these definitions, as well as governing equations. So when capital P is projected onto the camera plane, we are interested in their relationships, and Y would be equal to F times capital Y divided by capital Z, and X would be equal to F times capital X divided by capital Z. And that means XYZ is proportional to these two values, which is XC and YC. I say it's proportional because this is projected onto 2D plane, and we don't know, we don't exactly know the distance. What that means is, kinematically speaking, if you have any point on this line, any point on this line would project onto this PC. So you can't, if you know P X capital XYZ, then you can compute PC, but you cannot compute capital P from PC. You cannot go the other way around. So we usually say this, it's up to scale. It's accurate up to scale, and it's a matter of projection. So the mapping becomes linear if expressed in homogeneous coordinates. And this equation can also be described as follows. And this is just a vector matrix form of the above equation. And we need to add two more parameters into this matrix, which is U naught and V naught, which is the principal point. So there is two origin. One would be image referential, and the other one is camera referential. So originally, if the initial value was at the center, then we need to move that to this image origin for the image, which is image referential. So we need to add these two values to convert capital XYZ to map that onto small xy on the image plane. We have other parameters because this, camera sensor may not be perfect. Things there may be some skewness. For instance, if the let's say the image plane was skewed so that it looks something like this, then we need to take these things into account when it comes to intrinsic parameters. So this can be defined, the skewness, pixel skewness can be defined, modeled by parameter S, which is tangent alpha times F. So that leads to this relationship. And then the next consideration would be non-perfect, non-square pixels. So we may have pixels that are rectangular shape. Then we need to take that also count, so that that is introduced by this lambda value. So this is the intrinsic parameter, intrinsic matrix, where F is focal length, C is the principal point, lambda is the pixel aspect ratio, S is the skew. So that's the definition of intrinsic parameter, and let's move on to extrinsic parameter. Extrinsic parameter is the matrix that relates, if when you have camera that is in motion from one place to another, or you need to understand, you need to take the position of the camera itself. So when it comes to calibration, this will be necessary, and it'll play an important role. So this is the definition of extrinsic parameter, and the complete camera model consists of intrinsic parameter and extrinsic parameter. That way you can map the point P onto the image plane, small p. So this is these are the relationships, and usually this is called rotation matrix, and this is translation matrix. And let's start talk about calibration. To introduce you to calibration, we need to introduce you to homography. The referential is located in the 3D space, and if we use a checkerboard, 2D plane in 3D space, then Z would equal to 0. Points that are on that checkerboard would have the same distance, okay? And that would lead to this equation where M corresponds to the camera model, camera parameter matrices, K and R and T. And here, because we can remove Z if we use a 2D plane, such as checkerboard, then this equation size of the matrix and vector reduces. And homography relates 2D to 2D points. What that means is when you have capital P on this checkerboard, and you have that point projected on the image plane, which is small p, and we can relate these two points using homography matrix, which is H. We're going to call it H. And if we take a look at this equation and the description, capital H, this matrix has 9 entities, but has 8 degrees of freedom, since it can be expressed up to scale. In order to solve this, we need 4 pairs of point correspondences are needed. Projection can be rewritten into equation using cross product as follows. So, so this is because this is projection. This is you know, up to scale. We can you know, apply cross product between these two vector and matrix, and then that would lead to these equations. Okay, for one pair of point correspondences, meaning that if we have capital P and small p for one point, that would provide these two equations. And so that's 2 equations per one pair of points. And if we have 4 pairs of points, then we can build this equation, matrix vector in matrix and vector form. And the problem we are trying to solve is to find this H, which is the homography. Okay, so in summary, if we have 4 pairs of points, we can solve at least 4 pairs of points. We can solve for this homography matrix. If we have more, then obviously that would help getting more accurate homography matrix. By finding H vector that minimizes AH, 2 norm of AH, such that 2 norm of H equals to 1. And let's move on. So for each image of checkerboard, homography is computed. So now the homography is known. We know homography, and what but we don't know these values, okay? And using these constraints, so our norm of Rij equals to 1, and Ri1 transpose Ri2 must be equal to 0. So this is a dot product, and so this means that the vector length has to be 1 unit vector, and they need to be orthogonal. And using those two conditions, constraints, we can set up these two equations by plugging in these equations. Okay, so this is the resulting equation. So now we are left with H and K. Okay, so the equation now consists of only two variable, which is H and K. So we know H, and we did not know K. So that's the whole point of calibration. Calibration is to find these camera parameters, which is the K, the intrinsic parameter. So let's define omega as, let's define this as omega, which is this. Then the omega 1, 1, omega 1, 2, 1, 3 is as follows. And AC, it must be equal to 0. And then by solving this equation, we can solve for these intrinsic parameters. Okay, so it looks somewhat ugly, but it's not too bad. In fact, there are these camera calibration tools out there. Open source code codes are available for you, so you can use it for camera calibration. So this is a demonstration of ROS monocular camera calibration tool, and by moving the checkerboard, you can see that these parameters can be estimated in real time. Okay? And you're looking at the camera intrinsic matrix. Okay. All right, so that gives you camera model, camera intrinsic, extrinsic parameter. So when you put your cameras on a vehicle, you will need to do camera calibration, which means that you need to understand the internal parameters of the camera itself and where it's mounted, which corresponds to the extrinsic parameter. And then now let's talk about the detection, perception tasks. Now it's all about deep learning. Okay, so let's get started. So let's start with simple 2D object detection. 2D object detection has two sub-tasks. One is the existence of objects. Let me take that back. So one would be identify class of objects, and the other one would be existence of objects and localize them on 2D image using binary classification and regression. So this is more difficult than simple image classification. So image classification is when you have image and the task is to classify what the image contains. So usually that type of task is more suitable for small image with one object, but in reality that's not the case. Usually we have these many multiple objects in one image with a variety of classes. And for robotic applications, we also need to identify where this object is, okay? So, but because this is this localization is done in image space, this is 2D object detection. So using 2D bounding box, okay? This is still necessary for you know, traffic sign, traffic signal. You know, there are many you know, tasks requires 2D object detection task for autonomous driving. So let's talk about 2D object detection first, and then move on to 3D OD. So let's start with loss function. Because, like I said, because it has two tasks, it consists of two terms. One is the classification loss. The other one is the regression loss. So classification loss is to identify which class this object fall into, and the regression loss corresponds to how close where this object is and how close this prediction is when compared to ground truth. So it consists of two loss terms, and so you can see that classification loss is the multi-class loss used for many you know, classification problems, and L1 loss for regression is also very popular for a regression problem. So the idea is to minimize the error between the prediction versus ground truth position. Okay, and this is a visualization of the loss. So we want to minimize, obviously minimize the loss to optimize or train the network. Okay, and let's start with a quick history of 2D object detection. You know, deep learning based 2D object detection history of 2D object detection is not that long, because deep learning, you know, deep learning came into the picture for these 2D object detection only about, you know, about 10 years. So yeah, so after AlexNet, which was mostly a classification task, and then expanded towards many other tasks, including 2D object detection. So it's less than 10 years, okay, using deep learning. Before that, it was mostly conventional, traditional approaches. During this period, it started with two-stage detector. So there are two types, two-stage detector, and then there's one-stage detector. Originally, 2D object detection started from 2D two-stage detector. There's a region proposal network, and then there's a refinement network. So region proposal network roughly finds where an object is first, and then the refinement network fine-tune or refine the bounding box regression to get better accuracy and performance. But later on, this two-stage detector turns out to be somewhat redundant, and it's slow because it has two-stage. So later on, people proposed a one-stage detector. And initially, the performance wasn't as good as two-stage detector, but as time goes, one-stage detector performance of one-stage detector actually substantially improved, and now many detector uses one-stage detector. So let's start with RCNN, the famous early 2D object detection network, region-based CNN. So let's go through this bullet points. First, object detection method using CNN. Selective search used to find region proposals. Region proposals cropped and warped from the input image. AlexNet is used to extract features, but support vector machine. It was used for object classification and box regression. So what that means is the backbone, the feature extraction network was the AlexNet, but the downstream end towards the end of the network was using support vector machine, which is traditional methods. And then there was this reason proposal, about 2,000 proposals, and then use the AlexNet to sort of refine about the class, whether there is a object exists, and to compute the size of the box more accurately. So this explains, this slide describes that. The reason proposal was initially a rule-based method, meaning that it wasn't done by neural network. And then there were regions. The regions are cropped and resized into 227 by 227 size image, so that it can be used for the input for AlexNet. And then the AlexNet outputs provides 4096 dimension features, and then you use support vector machine for object classification and box regression. But this was very back then. This was very innovative work, provides high performance, but had these limitations. CNN and SVM should be trained separately. Whole pipeline cannot be trained end to end, and then the slow inference time was another problem. 2,000 region proposals should be processed by CNN, meaning that when you propose 2,000 proposals, then you need to put that into the CNN network, AlexNet, 2,000 times. Okay, so that takes a lot of computation time. So it didn't seem it was very slow. So people try to improve it, and then the next work was faster RCNN. And the proposed method was to basically the region proposed network was done by neural network. And then let's go over these bullet points. CNN features are obtained by applying CNN to the whole input image. 3x3 sliding window is applied at each pixel of CNN features. Anchor boxes are used as references and multi-scale anchors. Objectness scores and the predicted box coordinates are obtained for each anchor. So because now you're putting the whole image into the CNN network, it had problem in localizing the task. So what they introduced was this anchor boxes. So so you have this sort of grid, and then these work as a anchor in the image plane, and you use different shape and size of the boxes, and this is the called anchor boxes, and then that gives you this is the region proposal network. And for these anchors, you can you can train so that whether there's an object in this anchor boxes, and then you also compute this offsets. Because you used anchor boxes, it's not pixel level grid. Obviously, it would be a sparse grid. So in order for you to accurately predict the location of the box, you would need these offsets, box offset values such as delta X and delta Y relative to the top left corner are predicted. And you also have this loss for binary classification, whether there's an object or not, to first identify existence, because this is a proposal. And the way it's done is you compute IOU with ground truth with the prediction or proposal results. And if IOU ratio is lower than some value, then you count that as false. If it's above some value, then you count it as true. So that you can tell whether there's an object within the box. And then you have this ROI pulling. So you pull the features from. So once you propose these anchor boxes and identify that there is an object in this anchor box, then what you do is you pull these features from this region of interest, which is ROI, and then you put that in. Into the fully connected layer. So you have this ROI pulling layer. So you pull these feature from the backbone network, and then you go through this fully connected layer to train, in the case of training phase, to find the gradient, and then for inference time to give you the predictions. But there's one towards the end of the network, you have this sort of post-processing algorithm, which is called non-maximum suppression. NMS is applied to the outputs of both RPN and refinement network, because if you have these proposals and prediction network during inference, you will end up with many boxes that are predicted as outputs. So what you need to do is you need to select a box that is most accurate and corresponds to the ground truth. So the way it's done is you compute IOU again, and then you delete these boxes except for the one that has the highest confidence. So you only keep the bounding box with highest confidence, and remove outputs that has low confidence. Okay. So this non-minimum suppression helps you get better precision. So there is a trade-off when you apply these NMS. If you make this threshold really high, then you may remove too many boxes. So your precision may be good, but your recall may not be so great because you may not end up with any boxes. Then you're going to miss detecting that there is an object. Okay. I think I covered this in the earlier slides, so I will move faster here. And then let me move on to one-stage detector. There's a network called SSD, YOLO. Those are two popular one-stage detector. So if you look at two-stage detector, it was pretty complex. There's two-stage, there's a lot of anchor region proposal, and then refinement. So there's a lot of complexity, and the role of the region proposal and the refinement network seems quite intuitive, but then it's somewhat redundant, and it was slow as well. So people put efforts into making this into one stage detector without having this proposal network. And if you look at this SSD single shot detector, what they did was they used this CNN backbone, which is, better, larger backbone network, which is VGG 16 in this case. And what they did was they bring this, all the features that were computed in each layer. So here's the output of each layer features, and you use all of that features for detection. And it turns out that you can actually do pretty good job without having a two-stage detector when you do these type of sort of using full available feature information, okay, from high resolution to low resolution, or low level feature to high level feature information. The SSD still used this anchor box, so it had to compute, so it had to define these anchor boxes and find sort of offset values to refine, to more accurately predict the position or localization problem. I think I can move fast here. So I briefly talked about this earlier, so I will move fast here. And the key idea is to use multi-scale features. So like I said, it uses multi-scale features from low level to high level features for predictions. And let me move on. And later on, people actually came up with this network called feature pyramid network. So initially, the baseline was to use these multi-scale features for prediction, but later on, people proposed this feature pyramid architecture for backbone, and then this actually quite improved the prediction performance by having these feature pyramid looking type of architecture to so features now can be used for different perception tasks. So to provide you with more implementation details, so there are these backbone networks: VGG net, ResNet 50, ResNet 101, ResNext 101, and they tend to give you deeper, better performance, but usually slower inference speed. Right, let me move on. And so here's more implementation details. There's a data augmentation. So we talk about data sets, and distribution of the data set is very important. but usually, data set created by people, are not perfect, obviously, because we don't know what the distribution is when it comes to feature level type of distribution. We can only make a reasonable distribution with human perception type of features. For instance, seasonal change, lighting conditions, environment change. These are obvious to human, so we can make data. We can try to make distribution wide, meaning that we can come up with diverse data set in that aspect. But there's a lot more to distribution of the data set. When it comes to low level features. So people do different techniques with data, data augmentation. So improving this diversity. Sometimes it's also known as regularization technique, because the data is not sufficient, it's not diverse enough. Then sometimes we can regularize this network by data augmentation, meaning that try to come up with creating somewhat artificial data by augmenting the original data. So there's cropping, flipping, there are different techniques. And then you also need to do, you might need to do learning rate scheduling. So for instance, if the learning rate is too slow, then too small, then your convergence may take forever. Okay. If you use large learning rates, I don't know, if you go back to the lecture, I think 4, there was this step hyperparameter value when it comes to gradient method. If you use large value, then the gradient, but so you need to go to this direction, but the problem is how far. And if you use large value, then you may jump into the other side of this this sort of valley like function, and in worst case it can even diverge. If you use large values, you can go far far away from the optimal point. So best scenario is to use, maybe initially you might want to use relatively large value, but as you move towards get closer to optimal parameter values, you might want to reduce size of the learning rate, so that it converges and optimizes to the value. And then there's batch size. You can play with batch size depending on your GPU memory, and it also has a lot to do with your training speed, convergence rate, your size of the data set. There are many factors, so you might need to play with these things and just find the how things change when you change these hyperparameters. So it's it falls into somewhat domain knowledge or know-hows. Okay. So for instance, let's say let's take a look at example. So we fix learning rate here, and then we are playing with batch size. And you can see that batch size of 64 gives you the best performance. Okay, whereas you fix batch size, and then you can also play with learning rates. In blue, when you have large batch size, you might want to increase learning rate. So that type of things are trial and error based findings. Okay. Optimization. There are these optimization solvers out there. You can almost just use it off the shelf, but when it comes to training, you might need to play with many hyperparameters. Okay. All right. Let me quickly pause and move on to the next part. All right, let's continue. 3D object detection. 3D object detection problem is different from 2D object detection. Unlike 2D object detection, 3D object detection requires more information to predict. And this is where the challenge actually comes in when it comes to perception for camera-based perception for robotic or autonomous driving problems. Let's take a closer look. So detecting objects in 3D space means that we need to detect existence of objects, localize them in 3D coordinates. That requires binary classification, center position, 3D size, rotation regression. So if you go back to if you go back and look at 2D object detection, all you had to predict was these information. So all you need was the class and then 4 pixel coordinates, left top corner and then right bottom corner can give you the full information for 2D bounding box. But if you look at 3D objects, you usually use 3D bounding box, often called a cuboid. And that requires many more information. So this needs to be output of the network. So compared to 2D object detection, you need to estimate, predict more detailed information. What's making this more challenging is that, like we discussed earlier, camera image does not have distance information, and we need to find that from the context and estimate or predict them. So that's where accuracy drops substantially when you go from 2D to 3D object detection. So for 2D object detection, you get very good performance using many available backbones and headers networks in the literature. But if you go to 3D object detection problem, the performance is not as good as 2D object detection. So for 3D object detection, you need you need the position, and you need size of the box, and then you need to compute angle, heading angle, and then the class. Okay. And how do we evaluate the detected results, and how do we train them? Well, we compare that with ground truth, and if you look at the data sets that are available, they usually provide these information, okay? So that you can replay these ground truth for the logged raw data. And using those information, using the ground truth and the predicted results, we need to compute these values, recall and precision, to evaluate the performance. Recall is how many of objects are detected. Precision is how many of the predicted results are correct. So what that means is, so when you have these real labels, and if you have, so ideal case is that you have 0 false positives and detect all labels. So you want to minimize false negatives and false positives. Then you can get 1 for both precision and recall. So if you take a look at this figure on the right side, let's say there were these ground truth. We have 2 ground truth here and here, and let's say your predicted results have 2 bounding boxes that are shown here and here. And what this results mean, if you evaluate this, then this blue box is true positive because there is a GT here, but this red box is false positive, meaning that you identify that there is an object, but that's false. And then you also need to look at this GT, which is not detected. So it's false negative, meaning that you detected negative, no object, but that's false. So ideally, you want to detect 2 objects with good precision, okay? Right. So, and then there is a score, confidence, which indicates confidence in detection, which is often used for evaluating prediction results, as well as tuning and calibration purposes as well. So if you apply low score threshold, meaning that if you apply non-minimum suppression with score threshold of 0.1, then it's going to use almost most of the predicted results. So you see many boxes, but then it's likely that your recall will improve, but precision will decrease, meaning that there is a less chance that you are going to miss detecting an object, GT, but it's highly likely that you have more detected results that false, false positive. Okay, so that's what this means. So if you decrease score when you apply non-maximum suppression, then you can increase recall but decrease precision. So it's tricky how we need to evaluate the performance of this models. The way it's done is we compute average precision, and what it does is you draw this curve by changing this score threshold, and you will end up having these line, sort of multiple points, and if you connect them, then you will end up with this line. So because you change the score threshold, so you will, like I said, increase recall but decrease precision when you decrease score threshold. So here's recall, here's the precision. So when you lower threshold value, so you're going to go this way. If you increase threshold, then you're going to move, the performance will move towards that direction. You may have, model predictor that may have this type of precision recall curve. And the idea here is that let's compute area under this curve. Then that's going to be average precision, okay? And the idea is that when you have perfect perfect prediction model, then you will be able to reach this point, which is utopia, right? So you want your model to reach this point, okay? Then it's perfect model, but it's very unlikely that we will be able to achieve that this point. It will be somewhere close to that point. So we want to maximizing this area will be achieved by pushing this boundary to that point. Okay, that's the idea of average precision. And when we say mean average precision, that means we need to calculate this for different classes, okay? And compute a mean value of multiple average precisions, okay? And for Kitty data, there's easy, moderate, hard. For nuisance, you have one more threshold value for computing precision recall. That is the you need one more threshold value to, where is it? Well, it's not shown here, but when we compute, when we compute true or false for positives, we need some sort of threshold value. And for Kitty, data sets, usually that is done by IOU, intersection of union, which we talked about in 2D object detection. But and then for 3D object detection, same can be applied, but for nuisance data set, it's done by the distance between the center point of the GT and the predicted results. So when you have two, let's say you have two bounding box, so you can compute IOU based on, you know, how much volume is intersecting, or you can compute the distance between these two center points. Okay, so there are different ways of evaluating object detection performance. All right, let's move on to image-based 3D object detection. Image-based, camera-based perception can be classified into two approaches. One would be RGB approach, and the other one is depth map-based approach. RGB approach takes RGB image and directly regresses 3D attributes that we introduced earlier. And the advantage is computationally efficient and faster inference speed. But limitation is the localization accuracy tends to be lower. Depth map approaches usually takes depth map from depth estimation network, and you use different detector head. An advantage of this approach is more accurate localization results. The downside is it's computationally heavier and slower inference speed, because you need depth map estimation network. And one more thing is that you need more data to pre-train the depth map. So usually this we said this gives you better performance, but this may not be a very fair comparison, because usually when you train depth map, you usually do you use extra data to train this depth map. So and the performance depends on this accuracy of depth map. Okay, and this is network taxonomy. So we introduced two approaches, RGB and depth map approach. And there's RGB approaches can again divide it into two types, one stage versus two stage. And the depth map based approach could be divided into depth map based versus pseudo lidar. And this slide sort of summarizes different papers in this field and how things have evolved. If you read these papers, you will be able to follow them. Okay. Let's start with RGB image approach. One of the most popular one is CenterNet. The idea, motivation is it predicts objects as a key point, center point of objects. Use one by one feature as at key point to implicitly represent objects instead of n by n ROI feature map. Lift key point pixel to the 3D space using camera intrinsic. Key point representation can be simply extended to other tasks, such as 2D detection, 3D detection, and human pose estimation. So initially, this center net was proposed in 2D object detection community task, but then it later on it expanded towards 3D object detection as well, and it back then it gave us a significant performance boost. Let's continue with CenterNet. We need different losses, different targets to train CenterNet. We have classification targets, which uses Gaussian mask, and then we need regression target, which is the key point. So the idea is that we introduce this heat map using Gaussian mask so that the network can learn where the center is. So the GT provides the center point, and we need to apply this Gaussian mask, and it will provide a heat map, and then we can learn this position of the center point. And then we need regression head and targets to finally compute these offset, depth, size, and orientation. So those are not available when you only have this center point. Okay, so you need to have this targets and losses corresponding to them. So here we are summarizing the loss function. It's very similar to standard 3D object detection loss functions. Here, but the difference is that, like I said, there's this key point or center point regression, and then that is done by classification, and then we need to regress these values. Okay, so this classification loss looks for the position of the center point, and this box regression loss looks for the offset, depth, size, and orientations. Let's move on to depth map approach. The motivation is that image does not provide depth information. So and there's a whole community field for depth map estimation. So why don't we utilize and leverage this available depth map network, and then we can hopefully predict 3D objects more accurately. Okay. So accurate depth map estimation is the essence of molecular 3D object detection. Let's utilize depth map. 3D object detection network takes depth map as input. So you put input, RGB input, and then you using the depth map network, you can get the depth map output, and we are going to use that for object detection input, input to the object detection network. Okay. And one branch would be using LiDAR detector, and if you do so, then people earlier people called that pseudo LiDAR, because you're basically using LiDAR detector, but input was not the real LiDAR input. Instead, we are putting the pseudo LiDAR point clouds using depth map network. So that's called pseudo LiDAR. And the working principle is described here of the pseudo LiDAR. First predicts depth map using depth estimation network. And then in order to train this network, we need depth loss with ground truth. So here, this part requires extra pre-training and extra data for depth map training learning process, and that can actually be very slow and computationally heavy and require a lot of annotation jobs, because depth map is pixel level ground truth. So usually this is very hard to obtain, and usually you achieve these depth maps using LiDAR point cloud, and then you need to generate the full dense depth map human annotator in the early works. But later on, generating depth map GT, as well as training depth estimation network, was done by self-supervised learning using dense depth map ground truth using structure from motion. And we can talk more about that during discussion session if you're interested. And then we have depth map as an output of the depth estimation network, and we need to change representation if you are going to use LiDAR type of detector, so that the representation is now converted to bird's eye view or 3D space representation. So now it's point cloud voxel type of representation here. So here information was 2D image dense depth map. So pixel level, there is a distance information, but here you have sparse point cloud. Okay. And then using 3D object detection network, you can detect objects. Okay, so this was pseudo LiDAR approach. So I pretty much gave you summarized how the network works, and this is more details of that. Depth estimation network, which will be detailed in lecture 6, next lecture. So you get the RGB input, and your output would be depth map. And you would use the encoder decoder like network architecture, similar to semantic segmentation, because you're estimating pixel level distance. Okay. And the way to train this network can be classified into 3 types: supervised manner, and then there's a semi-supervised manner, and self-supervised approach. So you could use supervised approach if ground truth is available, but like I said, you know, creating this ground truth with many data can be quite labor heavy, time consuming job. So people usually, for semantic segmentation and depth map depth estimation, usually it's very the annotation job is very computationally labor heavy job. So usually annotation cost is high. So there's a lot of semi-supervised and self-supervised learning methods are proposed in those 2 fields. And here for depth estimation network case, luckily we can generate these depth maps using traditional computer vision 3D geometry theories in the field. So and that's one of that field sometimes called structure from motion, and we can reconstruct environment, 3D environment, using multiple camera inputs, either stereo. It could be either stereo or sequence of images. Once those informations are given, we can reconstruct 3D sort of depth information or point cloud. So leveraging this sort of principle, theory, we can sort of automatically generate ground truth, and then use that for training the depth network. By doing so, we can do self or semi-supervised learning methods for depth map training, depth map network training. And then we need, like I said, we need to convert depth map to point cloud representation using the camera intrinsic parameters. So depth map representation is dense, image, same resolution as image, and pixel level distance information is given, and it's image perspective. But when you convert that into 3D space, and now there's there will be point cloud in the 3D space, and if you look at them from another viewpoint, then it looks something like this. Okay. And you see this occlusion areas with black space. And then using this point cloud, point cloud in 3D space, you can do voxelization, meaning that you sort of create grid in the 3D space. So you have boxes that are in the 3D space, stacking next to each other, X, Y, and Z direction. So they are boxes, and when you remove the Z direction, meaning that if you voxelize with one box in the Z direction, then it becomes a bird's eye view representation. Okay. And point pillar is sort of working in that representation. Okay, and detector works in that bird's eye view space. That way, the network can run faster. Okay. Voxelization is described. And if you neglect the Z direction, if you neglect Z direction grid, meaning that if you just lump everything into the Z direction so that it looks like a pillar, then you can sort of apply 2D object detection because now it became 2-dimension from top view, okay, bird's eye view. So this is a visualization of pseudo lidar. So you're looking at RGB input and then depth estimation output and visualization of that in 3D space. And you can apply lidar based detector or 2D object detector, depending on your representation. Okay, this is it for lecture 5, camera-based perception part 1, and let's continue with camera-based perception part 2 in the following lecture. Okay, thanks for your attention, and see you next week.